In this video, we're going to compare the changes that adding a catalyst has to a kinetic energy distribution to the changes we would expect to see on a potential energy curve. As we know, the most important measurement on a kinetic energy distribution is Emin, because that represents the minimum amount of kinetic energy that reactant particles need in order to undergo a successful chemical reaction. When we add a catalyst, they decrease this minimum amount of kinetic energy, which we can represent by moving Emin to the left like so, and as a result, reactant particles need less energy in order to undergo a successful reaction and form the activated complex, which we can see on this graph due to a greater number of particles being represented by this area, showing that more reactant particles can undergo a successful chemical reaction than in the uncatalyzed reaction. We also know that Emin is translated to EA when referring to potential energy terms. Now, since catalysts decrease the minimum amount of kinetic energy required for a successful chemical reaction, that must mean that they would also decrease EA, meaning that if this represents the EA of an uncatalyzed reaction, maybe our new lower activation energy is only here, meaning that we could rewrite the curve. Let's draw it as a dashed line here to see the difference. We can rewrite the potential energy curve like this, reflecting the lower activation energy. Now, of course, not everything is this simple, because whenever we add a catalyst to a reaction, it's almost always going to change the mechanism, which is the movement of electrons between lone pairs and bonds that actually results in the reaction happening. And since the mechanism of the reaction is different, the number of steps or elementary processes within the reaction is also going to be different. So a more accurate way to rewrite this potential energy curve, let's say that the original reaction only had a single step, but maybe adding the catalyst results in this happening in 2 steps rather than 1. If there are 2 elementary processes, well, now our potential energy curve might look something like this. So here we actually have 2 activation energies, but we can see even if we've taken the original activation energy and split it into 2 steps, each of these individual steps has a lower activation energy than the original step, and therefore less energy is required in order to get to the activated complex of the rate determining step. Now, again, I said this is what it might possibly look like, because the only way to determine the difference in the number of steps or elementary processes from adding a catalyst is to actually look at the reaction's mechanism in order to predict this, which needs to be done on a reaction or to reaction basis. In the next video, we're going to be going over the final type of calculation in the thermal chemistry unit and looking at an explicit relationship between concentration and the rate of a chemical reaction.